Dear friends, today we will discuss the operating principle of brushless DC motor. In my previous lecture, we have discussed the introduction of brushless DC motor, in which we discussed the basic construction of brushless DC motor. So we have discussed the brushless DC motor has stator, brushless DC motor has a rotor, and rotor is consist of permanent magnet. Stator has armature winding, and these windings are excited according to the position of the rotor, and rotor position is sensed by the Hall effect sensor. So that part has been discussed earlier earlier lecture. So in continuing that, we will discuss operation or operating principle of brushless DC motor. So what we have discussed earlier in the previous lecture, so we have discussed the construction. It is consists of two parts, stator and rotor. So rotor is consist of permanent magnet and stator is consist of armature windings. So electronic converter is there, control system is there. So controlling is done by the signal received from the Hall effect sensor. Hall effect sensor gives the signal, and the closed loop pulse width modulation speed controller gives the signal to the switches of the electronic converter. That part was discussed in the previous lecture. So now we will discuss the operation principle of this brushless DC motor in this part. So going forward, we all know that the stator winding which are available on the stator, that is armature winding, it is star connected, and switches which are in electron converter are responsible for energizing the winding available on the stator, that is armature winding. So sequencing of turning on of the switches is very important, which will ensure the direction of the rotation of the machine. Whatever the torque developed or the direction of torque, it will determine by the appropriate sequence of the switches. So appropriate sequencing is mandatory for obtaining unidirectional operation, which is ensured by the unidirectional torque development. So for the development of unidirectional torque, appropriate sequencing is mandatory. The phase windings are energized in a particular sequence, which will determine whether the machine has to operate in clockwise direction or in anti-clockwise direction. Suppose in a case we want to reverse the direction of the machine, the switching sequence has to be reversed. So if particular sequence is giving clockwise direction, to obtain anti-clockwise direction, that sequence has to be reversed. So corresponding operation can be achieved. And these Hall effect sensor, they are responsible for obtaining the rotor position, and they senses the rotor position and gives the feedback. Corresponding feedback is achieved. This is the basic diagram how it operates. So we can conclude here, as we have discussed in machine part earlier units and real topics. The torque developed by this machine, equivalent torque developed by this machine, will be proportional to stator field flux, proportional to rotor field flux, and sine of the torque angle. So we know that the rotor is consist of permanent magnet, therefore phi r is constant here always, and only phi s is responsible, and sine theta is responsible for the equivalent torque developed. So if we consider phi s, suppose the current provided to the stator is constant, in that case the phi s will also constant. Therefore we can conclude that phi s is dependent on the current. So whatever the current, and you know that stator has three windings, three phase windings, phase A, phase B, and phase C. So the corresponding phi s will be resultant of all. So we can say that suppose field flux is constant because field is consist of permanent magnet, rotor is consist of a permanent magnet, and stator field is also constant because current is constant. Suppose current is constant instead of the time the current is constant, phi will also be treated as constant. So therefore the torque expression can be like this. So equivalent torque expression for phase A will be proportional to current in phase A winding and sine of the theta. And similarly, we can determine the equivalent torque for phase A, for phase B and phase C. This diagram gives you the Hall effect sensor output, current, back EMF and output torque. So you can see that output torque is a resultant of torque doubled by phase A, torque doubled by phase B, torque doubled by phase C, and so on. So the resultant torque obtained due to the phase A, phase B and phase C. So we can find the instantaneous torque doubled by all the three phases, phase A, phase B and phase C will be, suppose for phase A it will be Kia sin theta, for phase B it will be Kib sin theta minus 120 degree, that is a phase difference of 120 degree, and for C it will be Kic sin theta minus 240. So angle 0, 120 and 240. So this phase difference is there. And corresponding current will be sinusoidal. It is considered to be sinusoidal. So the corresponding current for phase A, phase B and phase C will be Im sin theta, for B Im sin theta minus 120 degree and for C Im sin theta minus 240 degree. So the corresponding torque will be for these phases, phase A, phase B and phase C is this. So for equivalent torque for phase A, Kim sin square theta, for B Kim sin square theta minus 120 degree and for C Kim sin square theta minus 240. So resultant torque will be equivalent torque. So it is torque because of A, B and C. And the resultant torque which we obtain will be 3 by 2 Kim square. So in starting we discussed the torque is dependent on sine theta, but from the resultant torque it can be concluded that shaft torque is independent of rotor position theta, and it is linear with respect to Im, the amplitude of the current, right? And this is also available in conventional motor. So motor torque developed in BLDC motor consists of pulsating torque, right? And these ripple contents are available in the torque. So this can be reduced by using 4-phase and 4-pulse and 3-phase 6-pulse BLDC motor. This will enhance the overall performance of the machine. Thank you. Thanks a lot.